Welcome to the first session. I'm really excited to be here and thanks for coming. Just a reminder, silence your cell phones, please, if you haven't. My name is Dr. Brent. This is my first year here as a professor in the chemistry department. I teach biochemistry, and I have 3 research students I'm really excited to have presenting today. I'd first like to invite up Gavin Cabral for the first presentation. Gavin is a sophomore and plans to go to medical school after his time here at USJ. So, Gavin, you have the floor.
Hello, everybody. My name is Gavin Cabral, and this semester I did research on high-throughput drug screenings of the GABAA receptor. So basically what our goal was this semester was to find new prospective ligands and scaffolds for ligands that would activate the GABAA receptor. So first off, what is GABAA? So GABAA is a ligand-gated ion channel. So basically what this means is when a ligand attaches to it, the channel in the middle that you can see right there, that big opening in the middle, opens up and it allows ions to pass through it. And basically what that does is it is the main inhibitory receptor of the central nervous system. So what this does is it will bring neurons within the central nervous system further away from their action potentials by hyperpolarizing them. This inhibits the function of the central nervous system. So GABAA has 5 main binding sites that we looked at this semester. And they would be between each of these subunits. So there's 5 subunits, 2 betas, 2 alphas, and a gamma. So going into this, we predicted that sites 1 and 3 would have some similar results for which ligands would bind to them because they have a similar configuration of that beta alpha for like the 2 subunits that meet at that section. Looking at this rotating image right here, these loops kind of like indicated where we were kind of looking for these binding sites. That helped us kind of set boundaries about where we wanted the ligands to dock. Which was very important for this research because without it, it would be a little bit harder to find those different binding sites. So currently there are a variety of GABAA effectors. The big 2 are benzodiazepines and anesthetics. So the image on the left is just the basic scaffold of a benzodiazepine. It has these 3 different rings and it has 4 different R groups coming off of it that can be a variety of things that would have different effects on how it interacts with the body. And then the anesthetics, as you can see in this image on the right, the receptor on the left is not activated, so there's not really allowing many chloride ions to enter the cell. But the receptor on the right it is binding to by propofol, and that allows the channel to open, and it allows an influx of chloride ions into the cell, which is going to inhibit function. So this is all important because currently stress and anxiety are very big problems within our modern society. And GABAA is a receptor that is a major target for a variety of treatments that can aim to tackle these issues. And also anesthetics are basically used in nearly every field of medicine nowadays. So it's kind of important to figure out new anesthetics because people react differently to the ones we have currently. So we want to be able to find ones that are suited for basically everyone because you don't really want to have any issues, especially with someone that is under anesthetics. So the purpose of our study, like I was saying, is to find new scaffolds. So currently we have of 3, these are 3 of the ones that we have right now. So GABA is the endogenous ligand for the GABAA receptor. So basically what that means is what's made inside of our body to activate it. As you can see, it's smaller and it has a charge in this case because it wouldn't normally have a charge, but in this case it has a charge because at the pH of the body, it would become protonated. And the other 2 we have here are flurazepam, which is a benzodiazepine. So you can kind of see that similar structure of the 6-membered ring, the 7-membered ring, and the other 6, and it just has 4 different substituents branched off it. And the last one is tiagabine, which is a drug that is used to help patients who suffer from seizures. So for the methods, we originally started off by gathering 1.2 million ligands from a couple of databases, and these range from 250 to 350 daltons in size. We went with this range because we originally did some screenings, and it came back that all the ones that bound to these sites were somewhere within that range, and we didn't really see anything that was larger or smaller than that size. So after we had these ligands, we used initial screenings to kind of see how they would act inside the body and see if they would actually be viable to begin with. So what we did was we filtered by oral absorption, toxicity, and their ability to cross the blood-brain barrier. Being able to cross the blood-brain barrier is very important because if you're going to have a receptor that is the main inhibitory receptor of the central nervous system. You're going to need it to be able to get into the central nervous system to begin with. And all this filtering allowed us to go from 1.2 million ligands down to 750,000, which we took into the next stage of our screenings. So this next stage was ligand docking, and basically what we did is we first found these binding sites. So as you can see through this image right here, that loop has kind of helped guide us to it. And that purple box is basically the parameters that we set of where we think these ligands should be able to stick. So we threw these 750,000 molecules at this binding site and saw how they reacted and if they had a good fit. So these screenings, we had 3 different types: HTVS, SP, and XP. So these varied in their actual rigidity of the structures that we were using. So HTVS was the most rigid. So it wouldn't really act how a receptor would act in the body, because in the body, when a ligand attaches, that receptor will morph to it so that it has a better fit. So then as we moved up to SP and XP, they become more and more fluid, so they're going to start acting more like how they would act in the body. So what this allowed us to do was start with HTVS, narrow down the worst ones, so take it out, and move our way up to XP, so we had a smaller sample size to run the XP at, because each one of these takes progressively more time to run. So if we started with 750,000 with the XP, it might have taken a month to run all these molecules. So after we did this, we filtered down the molecules to roughly a couple thousand, and that's when we kind of started able to analyze them directly. So we used Excel to start to analyze them and see which ligands dock to more than one site, and those were kind of our best hits. So what we found is, like as we predicted, that sites 1 and 3 had a variety of hits that were in common, while they had really nothing in common with sites 2, 4, and 5. So these 5 ligands on the right are some of the scaffolds that we saw. These 3 right here, as you can see, are all very similar. They only differ in stereochemistry, so how those OH groups are kind of oriented off of the original molecule. And then the 2 on the right, they're kind of similar to each other as well. They have a 5-membered ring and some different R groups, but those are just some of the scaffolds that we found. Overall, one of the other big common things that you can see is that all of these are charged. And so what being charged means is that they can form salt bridges in the body, and that really helps to stabilize the interactions and make it stronger. So moving on to the next sites, we found that 2, 4, and 5 had some hits between them as well. They had 8 total hits that were common for all 3 of the sites. These ones are slightly different. They're slightly bigger than the ones we saw on the last slide. And they each have those 6-member rings, just different orientations and how they are. But as you can see, these also all have that positive charge, which, as I said, helps to form those salt bridges. So basically, that was what we were able to do this semester. What we're aiming to do in the future is we want to actually go and buy all these molecules, and then after we buy them, we're going to run assays on a cell line to determine if they are able to actually bind to and activate that GABAA receptor outside of these screenings. We already have a grant to do so, and we're going to buy some of the molecules that we showed on the last slide so that we can kind of go and test them and see how viable our actual findings were. So these are kind of like the list of the ligands that we want to go and look at. So the big thing here is that some of these are very good hits, but some of them also have some problems with the actual other data that we found. That means that we're going to use it more as a scaffold to see if we can adjust other parts of it to keep that ability to bind to GABAA, but maybe take away some of the negative qualities. So for example, this receptor this ligand right here, you might not be able to read it from further back, but it has a hERG value of -7.295. And really what that means is that it is something that hERG is a value of how toxic in a way that ligand is going to act inside the body. So having a -7 value means it might be a little bit too toxic to really want to use for a type of drug. So it's something that we might want to adjust in some ways after we see if the scaffold is viable. And the other big ones are the top 4 from the right up to here. They all have a CNS value of -2. That means it's going to have a difficult time entering the blood-brain barrier. But like I was saying, if we can modify some of the constituents off the actual scaffolds, we might be able to have find a ligand that will better enter the central nervous system. And overall, that's what our research. And I would just like to thank Dr. Brandt and then Jarrett and Jose as well for their help this semester. And that would be. any questions?
Quick one. When you screen these early on, when you started with a really large number, and then you determine, well, this is too toxic, and this one can't cross the blood-brain barrier. Where did all of that information come from? Was it other folks that had done that? Was it completely, done with computer modeling? And how much of it did people figure out from a wet lab where they actually have
So,
the molecules?
Yeah, so a lot of this actually came from, so this was all based on like our actual screenings. So we used Maestro for the large part of this. And Maestro has a variety of different like screenings that we can do that will give us a variety of different like output of data. So these references all come from research that Dr. Brandt actually did himself. So he's kind of like our expert on this. So he helped like guide us through it and see like which values were important. These screenings gave us a lot of data. So the ones that I mentioned, the CNS value, which would be its ability to cross the blood-brain barrier, the hERG, which would be its toxicity, and its oral absorption, which was actually just oral absorption. Those are the ones that he had us focus on, and that's what our screenings actually gave us. So he kind of gave us like those set points. So for hERG, for example, our cutoff was typically around a -6. From my research, we went a little bit bigger because our sample size was much smaller than what Jose and Jarrett started with, because we had like a certain size range. But overall, a lot of it was guided by research that Dr. Brent has done in the past.
To answer your question more specifically, those values are not based on wet lab chemistry. Maestro compares similar structures to actual wet lab chemistry and tries to make predictions based on that. But these are not determined in a wet lab.
Okay, but that's still really pretty good.
Yeah.
It does have that kind of.
It's pretty nice, yeah.
So basically, Maestro has something written up in code that simulates what's required to cross the blood-brain barrier, and then it's looking for certain features of these molecules with these ligands on them that could or couldn't pass over that.
Yeah.
Okay.
That's exactly correct. Yeah.
Can you maybe say a little bit more about what this is a therapy for and why you think it's needed? Like, that we can do it, but why is it a good thing?
So yeah, so at the start, so like I was saying earlier in the presentation a little bit, so these are aiming to activate GABAA. So GABAA, we want it is an inhibitory receptor, so it can help lower levels of, it can help with, so an overactive GABAA receptor can lead to problems with stress, anxiety, and in some severe cases it can lead to seizures. So basically by inhibiting it, or inhibiting neurons, we are able to, or an underactive GABAA receptor would lead to those problems. So by being able to find drugs that can activate it, we can look to aim to create medications that can help people deal with stress, deal with anxiety, and in those extreme cases, help prevent seizures. And then anesthetics are the other big thing that could be for therapeutic use. So, for example, my grandmother, under the common general anesthesias that we have now, she doesn't really wake up from them. So being able to find new anesthetics that might be able to negate those effects of the current ones can always be a huge benefit, especially considering that nowadays anesthetics are used for nearly everything. And that would kind of just be like what they can kind of be used for. But in this purpose, we were just starting to look off for like the ligands that could be used in the future. We're not really at a stage yet where we can actually figure out how well the effects of them would be.
Okay, good, thank you.
So I came in kind of as you were getting going, so you might have already touched on this a little bit with introduction and stuff, but how does all this fit with where you want to go with your career in the future? What are you looking to do, and how does this kind of tie into that, or what have you taken from it?
So I want to go into medical school someday, so kind of the actual effect of how it, like, so the development process is something that is really interesting to me. It's kind of made me think about actually going into the research side and pursuing research as well as medical school in my future. But overall, like, just seeing how it kind of can affect like a patient, how like it can help people find like just like a easier and better life. There's so many like uses that this could have, and to start like this process right here, you can at least narrow down how these drugs are going to affect somebody a little bit before you actually start these trials. So at the end of the day, it can also help prevent some of those drug trials that don't go too hot because something wasn't properly completely screened. because it has a completely new approach to how like drugs used to be developed.